Good afternoon, everybody. My name is Vanus Free. I'm representing today, or will facilitate today's talk. I was in the Free State for the last week, and they requested that, as chair of the Groundwater division, that I've actually facilitate this session. Welcome everybody to this wonderful talk. It's the 9th talk, if I'm not mistaken. And I saw that some of the guests that's on the members that is that listening today is actually from outside South Africa. I saw Denmark, I saw Lesotho. So that's very good. I first like to welcome our guest speaker today. That's Nicolette Vermaak. She was with the department for a number of years, I think more than 12 years. And I had the privilege to actually work with her quite a long time. Today she is now with the University of the Free State, busy with a doctor's degree, and she submitted the last version not too long ago. Today she's going to tell us more on the big problem that we have on building conceptual models. How do we start with one piece and actually building it up to the bigger picture that we can actually have? So from the central branch, I would like to give it over to Nicolette, that she can take us through this presentation. But just before she doing that, just a quick house rules. Please mute yourself, and then also your camera, that we can actually just save some bandwidth. And then please use the chat for your name as well as your affiliation. And if you have any questions, also please just type it into the chat, and then she can answer it afterwards. Thank you very much. Nicolette, over to you.
Good afternoon, everybody. For me, I loved building puzzles as a kid. And as I started working in the department, I realized that groundwater is very much like a puzzle. So in the end, this is kind of putting something that's fun and connecting it to something that we're working with every day. Our overview for the talk today is: what is a conceptual model? What is the background information that we need for the conceptual model? Some generalizations and assumptions that we often make that might cause us some problems. And then I'm going to share with you something that I've learned about the West Coast aquifer system. It's not a complete conceptual model yet. There's still new information that we need to add, but this is going to share with you how I see it from my experience and what I've learned from other people and from the monitoring that we've been doing at the department. When you start your scientific education, you learn about the scientific method, which consists of making a hypothesis that you go and test, and then you find out whether you are correct or not. And then you have data to back up your hypothesis, and then it can move to the next stage in the scientific process. And yes, I know my conceptual model can still change as we get more data. And I'm not gonna, my brother used to tell me about this scientist that committed suicide because he kept disproving his hypothesis. So guys, if you've got new information that disprove part of my conceptual model or even the whole one, I don't think I'm going to go that far. I'll still admit that I've made a mistake. For a groundwater scientist, their hypothesis consists of a conceptual model. A conceptual model is a pictorial representation of the groundwater system in terms of hydrogeologic units, system boundaries, including time-varying inputs and outputs, and hydraulic as well as transport properties, including their spatial variability. This is one of the formal definitions for it. Now, as groundwater scientists, we're in the unenviable position where we cannot go and reproduce our system completely in the lab. We're working with a system where we only have oral data and geophysics and things that gives us something of a picture or a window into what's going on below us. So I've been reading a little bit about stream flow and morphology and how people took these little models to the lab. Groundwater, you can kind of build a model, but it's never exactly the same as what you have outside. And because of that, we don't have just one parameter that we test in our conceptual model. We've got more than one, and it makes it a lot more complex than most other scientists. So this is where it comes to building the puzzle pieces. When we grow up, we learn a little bit of biology at school and a little bit about geography and a little bit about chemistry and a little bit about physics. But as you get into groundwater, you realize you need a little bit more about hydrology, information about hydrology and geomorphology and sedimentology and a few other puzzle pieces. But working on a conceptual model, that is just the tools that you get to work, build the conceptual model. The data that you need that you look at sometimes don't look as if they're really fitting together. Just like my puzzle pieces on this slide doesn't really look like it's fitting together. But if you have some information on my experience, it might make a lot of sense. So this is some of the background information that you need. First of all, maps. Just before I continue, sometimes you've got a lot of background information and sometimes very little. It depends on how important that area was, how many studies had been done. So, but the Council of Geoscience have at least provided us with some geological maps, and we have topocadastral maps. That's one of the first tools that we can use. Then, as I said, depending on the amount of research or studies that had been done in an area, you might get quite a lot of reports. Now, there's sometimes consultant reports. That is work that they had done for their clients, for government, for whoever their client was. And then very often there's also departmental reports. Some of them are available to the general public and some of them you have to have special permission. And then of course there's hydrocensus data. A hydrocensus is where you go and do a recording of all the water-related infrastructure that you find in an area. In our case, it will entail a lot of boreholes and springs and related groundwater geosites. And then, of course, climate data. Very often we don't think about climate data when we build the conceptual model, but that is where you get your basic information on how the rainfall patterns and the recharge can relate together. Then, of course, we've got monitoring data, water levels and water quality. And sometimes I feel very sad when I know a project has come to an end and there's no continuation in the monitoring, because the only way we can really get an indication of what's going on in a groundwater system is long-term monitoring data. So in some way, I wish we could continue with monitoring even when a project has ended. Then, of course, there's other information that we need. land use, because land use again will affect your recharge. It can affect your even your flow and discharge of your groundwater system. Soil, because when you have recharge taking place, that is where the water goes through to percolate towards the groundwater water table. And then I mentioned the sedimentology and the morphology, especially if you're sitting with an alluvial system or a paleochannel, as I had worked on in the West Coast around Saldanha area. That's all tools that can help you understand your situation a lot better. And then vegetation, because that also affects your infiltration and your groundwater system. Something people don't often think about is photographs, because that gives you a pictorial idea of what's going on in an area, and you can see how things have changed. And it's actually sometimes very interesting when you drive through an area like the West Coast shortly after a fire. It looks like a desert, and your routes no longer looks as clear as it had before. And one last piece that people often overlook is your information you get from your landowners, from people that's worked in the area. And sometimes it's very interesting. It's like I was talking to a game ranger in the West Coast National Park while we were doing a hydrocensus along the Langebaan Lagoon. And he told us that the water quality in the dug wells along the coast vary in quality. And if you go and check, it might link to the tides in that system. Also, the water levels seem to fluctuate together with the tides. So that's the kind of information you can get from people that know their area, that's lived there, that learned from what they've seen around them. The next point that we're looking at is generalizations and assumptions. When we're taught groundwater science, there's a couple of things that come with the territory. One of the first ones is that groundwater levels follow topography. And because of that, you would have a no-flow boundary at the topographical high. And another thing that we often do is we tend to see deposits as sandwich layers. I will go through a couple of examples where this basic generalization of your groundwater system does not quite work out, and where you have to make sure that you understand your system properly. Now, I have to add in a disclaimer here. I'm not a geologist. I only have 1 year of geology behind my name. So most of what I'm sharing here is things that I've seen in the field, things that I've experienced. So this is one of the first ones. One of my boreholes in the West Coast with the deepest water level of about 51 meters below collar is G30925. There's another borehole right next to it with a slightly different water level, but it's exactly the same, which means dunes do not follow the rule of water levels following topography. And if you understand a little bit about wetlands and the science related to that, you'll understand that would explain your dunes like wetlands. I have to add that these dunes have, if you go and look at the borehole log, it's layers of sand and calcrete. The calcrete most probably developed because of the chemical deposition as a result of the mist that comes from the coast. And that is what keeps this dune stable. The next one is another example in the area that I've worked, and it's incidentally this area where that was the subject for my master's degree, where you have a mountain range, and everyone tells you, if you look at the screen, your area on the left-hand side will have the highest rainfall and runoff and everything, because that is where your prevailing winds take the water, the rainfall, because rainfall in the Western Cape is mostly of orographic characteristics. But if you go and look at the geology map, and you look at the inclines of the layers indicated on that map, that is more or less the layering that you should more or less get, which means that, yes, you get most of your rainfall on the left-hand side, but it moves through the layers to the right-hand side. By the way, that green layer is Cederberg shale, for those that know a little bit about the TMG. Which means that, again, groundwater levels does not necessarily follow topography. And the next case is in close proximity to the previous one, where a consultant told the client to the left of this sketch that, don't worry, there's a topographical high. The water in the dam will not reach you and affect your vineyards. But he apparently did not read the engineering reports that came from before the building of the dam, where they found that there's a boulder channel connecting the dam with the valley in which this vineyard is situated. And there's a through flow of about 29 cubic meters per day through that boulder channel towards the vineyards. And they could not seal off or grout that boulder channel because of the pore spaces. So again, you kind of have this idea of the topographical high and no flow boundaries, and the real case study case does not show exactly the same thing. So that is a real life experience on where the first point of the no flow boundaries and the groundwater levels following topography does not quite fit. Some of you, through your experience, might have found a few more. Maybe we can put it all together one day. The next one is drawing layers as sandwich layers without considering the deposition of those layers. Now, this is an example from my study area that I'm going to present to you a bit later. And we tend to show the sediments in the paleochannel looking like that. And we forget that these sediments were deposited firstly in the Elandsfontein case under the through the river that flowed through that paleochannel. The second part, an estuarine situation, and the Varswater formation, and the Langebaan formation was deposited mostly by wind. So you kind of need to understand the position of your sediments, and that's where your morphology comes in. Okay. I'm going to look quickly at the case study, and because of the examples that I've showed you before, it's very clear that one of the biggest drivers of groundwater flow is not topography, but geology. So you do need to understand your geology. And if you don't really understand the geology and your groundwater system, and your conceptual model will be completely wrong, and then building a model from that, you're wasting your time and your client's money. So in the case study, I'm going to look a little bit at the geology and concentrating on the paleochannels, the stratigraphy, and the faults and other geological features. I will also look at water levels and water quality and how these can sometimes show you links between systems that does not look clear from the start. This is the surface geology for this part of the study area. And there's a line broken here and more solid that indicates the Colenso fault. It shows it as a single line, but most people will tell you it's a system of parallel lines with additional offshoots from that system. There's also another broken line that Woodford put in, and that is where the Malmesbury Shale and the Cape Granite meet, which means you will have a system where you have baking and fracturing along that contact, which if you understand a little bit about groundwater, and I hope most of you do, that can create the preferential pathway for the flow of groundwater. In the middle of that map is where we have about the Langebaan Road wellfield. And as you can see, Woodford divided this area into management areas. One of the other features for this area is the amount of calcrete. Calcrete tends to be lenses, and most people don't think that it plays a very important role. I'm still looking into it, but I tend to believe that the calcrete actually plays a very important role in this specific system. Firstly, in that it can protect the upper layer from the salt spray from the ocean, because there's areas there that actually have very good quality water in the upper aquifer layer. The second one is that it can kind of create the kind of semi-confined system in your upper aquifer layer as well. And some of the water levels that we've seen and the reaction to abstraction tend to confirm this. Sorry, the picture on your left-hand side is not very clear, but there's a gray area that indicates at the top that indicates the Langebaan Road paleochannel, and at the bottom for the Elandsfontein paleochannel. This work was done in 1982 by Smith. And Timmerman, when he studied the area further from about 1984, used this work extensively, and he did most of his drilling based on this information. If you look at the work of Smith, the paleochannel actually runs straight through towards the ocean, or the bay or the lagoon. While the illustration on the right-hand side, coming from Woodford's work, seems to indicate that the paleochannel ends before it reaches Saldanha Bay. And it's actually interesting to see the different basement topography that we get from the different scientists that work in this area. I'm going to show you one more illustration of the paleochannels, and you'll see it's actually fairly similar to the one of Woodford on the right-hand side. And it also uses the no-flow boundary idea that Timmerman used in his thesis and in his reports. This comes from work that Untitled did for the department. And one of the big differences between this and the work done by Woodford is the fact that the paleochannels goes right through either to Saldanha Bay or the ocean. And I think that was actually an improvement on the huge improvement on the Timmerman conceptual model. And we're quickly going to look at the stratigraphy. This is one of the boreholes, S1, I think, that they used to classify some of the formations in this area and determine the layers. And this is one of the results based on that stratigraphy. It's part of the conceptual model that was developed, trying to explain some of the observations that was made based on the boreholes that was drilled. As you can see, it does have calcrete lenses for the upper aquifer, but it has a almost continuous thick clay layer between the upper aquifer and the lower aquifer layers, and a basement high between the Langebaan road system and the Elandsfontein aquifer system. But if you remember, there's a shale granite contact that goes through this area, which means that there might be something that links the two systems. And that's one of the things that I started looking at, and that I'll show you when we look at the water levels. This is coming from work that Woodford through SRK did for the West Coast District Municipality, trying to find alternative groundwater resources for the area. And you can see again the Colenso Fault running in a northwesterly direction with some offshoot faults on the side. And then you have the Hoek fault running into the Piketberg-Wellington fault. So there's at least two big fault systems in the area. But because of the sand in the area, we have no idea of exactly where the faults run or how many other additional faults might be in the area. And we tend to then think that we only work on what we see, so there shouldn't be any other faults, but it might need, might need to look at it further. Then of course you have got your granite platons, the Vredenburg Saldanha platon at the top, your Darling platon more to the south, and your Paardeberg platon around Malmesbury. And these all play a role into the groundwater of the study area. Now we come to the water levels, and this is an example of borehole G33327. It is around the close to the West Coast Fossil Park, some distance from the well field. And I've plotted it together with the abstraction rates from the well field so that you can see the link between the two. I think it's about at least 5 kilometers distance between the two. And you can see there's almost a direct correlation. Just for a bit of background, we begin with historical groundwater levels. And I only started this graph from around 2001 when the monitoring in the area restarted again. And you can see the drop in water levels when the abstraction started in November or December 1999. And there's quite a huge drop. Original modeling said there would be only a 5-meter drawdown, and it ended up being about 11 meters. Then around 2004, people became worried about the abstraction in the area and the effect it has on the water levels of the aquifer. And they had to repair the pump. So for 3 months, they didn't abstract groundwater. And you can see the recovery because of the rest period. Then in 2007, we had a fairly good rainfall year in the Western Cape. And you can see some recovery around that time. And then 2008, 2009, you have the peaks from the artificial recharge pilot project that was done by CSR for the Department of water and water affairs and forestry at that time. After the artificial recharge stopped, you can see the drop in water levels again till about April 2013, when vandalism caused huge damage at the well field and they couldn't abstract. The next drop in water levels comes around 2017 when the drought started hitting the Western Cape, and the Saldanha municipality had to abstract more. But Saldanha municipality wasn't the only people abstracting groundwater at the time. We do not have a complete record of who else was, but I know there's at least one landowner in the area that started abstracting quite a lot. That's just a quick story, what I can pick up from this graph. And if you understand what the graph is telling you, you can get a lot of information out of it. I had a colleague that said that a 3-year-old can do water level monitoring. And it's not impossible, but a 3-year-old will definitely not understand what the water levels is telling him, and he wouldn't be able to interpret it. I started noticing interesting drops in water levels in the Elandsfontein aquifer that seemed to be linked to the well field abstraction. And I thought I was the only one that noticed it till I got to this graph from Alan Woodford's work. And yes, it's not a huge drop in water levels if you look at the water level contour there, because it's the 0 line. But the borehole at the bottom, G33320, is in the Elandsfontein aquifer, not Langebaan Road, and you can see the abstraction has actually affected it. This graph comes from around 2003, which means that it's about 4 years after abstraction started at the well field. This graph plots 2 water levels from Langebaan Road aquifer and one from the Elandsfontein aquifer. The medium blue water level is from G45635A. It's at the bottom of the well field boreholes, the lower, the one further south. So it's very close to the well field, and you can actually see the same pattern that I showed you from G33327, which is the dark blue curve here. The light blue curve, more turquoise in color, is from G33317. And you can see from around 2000, there was a drop in water levels. It was a very steady, slow drop, except around 2016. And you can see there seemed to be a correlation, very attenuated, but there seemed to be a correlation with some of the possible impacts from the well field abstraction. This is looking at water quality. I plotted stiff plots. This is only for a selection of the boreholes. We sampled originally about 42 boreholes. We reduced it to 25, and then as my thesis started picking up, we increased the sampling to include some of the areas that's never been sampled before. But one of the interesting things is you can actually see how some of the stiff plots group together in shape. Sodium chloride being the dominant components here. But if you go and look at the shapes of the stiff plots, there's an interesting correlation between the one for G46105, which is supposed to be a basement aquifer borehole at the well field to monitor the effect on the aquifer, and G33317. G33317, I think Timmerman messed up a bit because he put screens in both the upper and lower aquifer layer. And it's possible that they tried to make 2 different boreholes, but the other one collapsed because years after I started working at the department, we had a bit of a land subsidence close to this borehole, and it had the shape of a borehole where the ground dropped in. But G33317 should be a lower aquifer borehole mainly. And if you look at the link between the basement aquifer borehole and the lower aquifer borehole in the shape here, it seems to indicate that there's a possible link between the Langebaan Road aquifer and the Elandsfontein aquifer, most probably through the shale granite contact. There was some work done around it, but it's still fairly inconclusive, and it might need to be studied further. I'm going to quickly give you a bit of overview of my conceptual model. It is when you start building your conceptual model, the areas that you have a lot of information, you can build a model with a fair level of confidence. The further you move away from your study area and the less data you have, the more fuzzy it becomes. So what I'm going to present to you in the regional model is how I see things, how things could possibly work. It's not conclusive, it has to be taken further. But since I've worked in the whole of the Berg catchment, I started putting puzzle pieces together. Some do not fit properly yet. Some of them fit a bit better, but this is still work in progress. And then I'm going to move towards the local area where I have a bit more information. This is a drawing that I made from a proper map, just to be able to give you some information that wasn't on the map and to sustain some of my understanding. I spoke to a guy that was actually in the oil industry, and he used some of the information that he picked up from his work in the oil industry, and he started applying it to groundwater. And we had a very interesting conversation in November 2016, which is why I told you that listen to people that have interesting observations. They might help you understand things a bit better. He told me from his experience that there must be at least 2 fault lines going through the Atlantis area. The one, he said, had the crust zone of about 1 kilometer, while the other one going through Dussenberg was about 3 kilometers in diameter. And from what he told me, these fault lines was running alongside the Colenso fault line. And I tried to draw it in here. It's not very clear because it's green. That's the one line, and that's the other line. If you look at the geological map, you'll find that there's almost like a fan of fault lines starting in the Franschhoek area, and then they disappear below the swell. And that's kind of what makes it so difficult to get the connection between the Franschhoek area, the Darling area where it daylights, and Vredenburg, Paternoster area. There's a few other places that it's also visible, but it's difficult to link up the lines if you don't have actual surface areas where you can pick it up. Then, of course, you've got your Wellington-Piketberg fault system and your Milnerton fault that we heard about recently with the tremors that the Western Cape had, but from the position of the tremors, they're not close to the Milnerton fault, they're actually closer to some of the lines of the Colenso fault system. Then, if I saw a more recent geological map, 1 in 50,000 scale for the Groundwater aquifer area, and it actually, and for the Saldanha area, and it actually had a couple of more inferred faults that's not on here. And one of them is one running in the middle of the Langebaan Lagoon, and one that was running almost perpendicular to the Colenso Fault system through this Saldanha Bay area. And these were noted by R. Meyer. I'm not sure exactly who it is, and I haven't been able to find the source material yet, but there's a few more possibilities for recharge for this area, because one of the things that I started thinking about is the soil in the West Coast is actually very water repellent if it's dry. So if you don't get enough rain to over a long period to wet the soil, you don't actually get a lot of local recharge. And Yaconel actually picked it up in the Sunveld that most of your recharge comes from the mountains. And I thought maybe we have something similar here. So you have two possibilities for recharge, one from the Franschhoek area through the Colenso Fault system, and one through the from the Piketberg Fault system through the inferred fault that was indicated on the new geological maps. I'm not sure if they're available to the public yet. The last I heard they were, but I didn't have a copy of it yet. I just had quick photographs that I took at the time. And then, of course, you have the shale granite contact that will definitely, from a groundwater perspective, play an important role. So this is on a regional scale. It's very fuzzy. We don't have a lot of data to back up some of my what I've shared with you, but that's some of the things that's the puzzle pieces that don't quite fit yet. This is a cross-section through both the Elandsfontein and the Langebaan Road aquifer system. The Elandsfontein, by the way, Elandsfontein with the EI is the spelling that they use for the aquifer system. The Elandsfontein with the Y is for the formation, just to be able to differentiate between the two. Otherwise, it gets very confusing. As you can see, the Elandsfontein aquifer system is actually deeper than the Langebaan Road aquifer paleochannel from the records that we do have. And for most of it, we tend to portray it in this way that I've got it here. But if you go and look at your other factors, you might find that this is an oversimplification. I will show you another drawing that I did later on to explain. This is a cross-section coming from the mountains above Aurora to Saldanha Bay, and the area to the right of the Berg River is the Addenboerskraal aquifer system, and to the left of it is your Langebaan Road aquifer system. You will see there's a similarity in formations between the two. Work from the Council of Geoscience have indicated that the paleochannel from the Langebaan Road aquifer actually connects with one of the paleochannels for the Addenboerskraal system, which indicates that it might have been an extension of the Berg River paleochannel. This is just a pictorial explanation of what I've seen, and unlike most conceptual models, I didn't put any numbers or flow or anything on this. It's just to show you a little bit of how we see what's going on there. Most of the water levels in this area is very shallow. Even the lower aquifer water levels is sometimes similar or higher than the lower upper aquifer. If you understand a little bit about the deposition occurring in a river, especially in a meandering river that might even be also be a braided stream, you'll find that your gravel, your clay, your sand does not always get deposited on exactly the same spot. Your gravel tend to be transported further than your sands and your clays because of the particle size. and it also depends on the velocity in your stream. And I started playing around with the idea of a meandering stream and how the sediments get deposited. And I got to this picture where in the end, you might find that your gravel might be different layers of gravel on top of each other. So you don't always have a clay layer separating your gravel from the next deposition layer. And you might find that G30878, which is the type borehole for the Elandsfontein Formation, was drilled in exactly the same right spot to be able to get the three upward fining layers that Timmerman describes in his thesis and in his other work. So that's why I drew in the borehole right in the middle of the paleo channel. Recent work done around where the new Elandsfontein phosphate mine didn't quite go through, seemed to get to the clay layer or all the layers that was indicated by Timmerman, and people started questioning it, but it's just possible that the location of the mine was slightly off the main channel for the paleo channel. And that's some of the things that we still have to figure out, some of the puzzle pieces that's slightly missing still. And I'm hoping that the airborne geophysics that Saldanha Bay local municipality had done recently might shed some light on this and help us to build a better conceptual model for this area so that we can get to a better understanding of the system. Thank you very much for listening to me. I hope you've learned a little bit. And that you've seen that building a conceptual model means that you have to have a fairly good understanding of your study area so that you can then recommend management and build a model and whatever else you need to do for that study area. I'm ending with some West Coast flowers. I understand it was very beautiful this year and I was unable to go and see it. Any questions? If you put it in the, in the comments, we will look at that now. Thank you very much.
Nicolette, thank you very, very much for a very interesting talk. Yes, I've also learned a few things that you mentioned. Yes, but thank you very, very much. I see that Matthew posed a question in the chat. You can maybe answer that one. And then anybody else that would like to pose the question, that can also put it into the chat. Thanks.
Francis, I don't quite have access to the chats. Can you maybe read the question for me?
Yes, I can do that. So thank you for a great presentation, Nicolette. Very well prepared and insightful. You mentioned the inclusion of climate data in your conceptual model. Should we include potential climate change impacts, for example, decrease in recharge in the conceptual model, or should this only be brought in at the predictive modeled stage of a project?
I'm not exactly sure. I didn't quite look at the climate data specifically here, but for me, climate change is an important thing that will affect our management of an aquifer system, but it's not necessarily going to change the conceptual model per se. It will change the recharge going into your conceptual model, yes. So that is where long-term monitoring data is extremely important, because that will already give you an indication if there's a possibility for climate change. Just for interest's sake, most climate models indicate that the west coast of South Africa will get drier, higher temperatures, less rainfall. So yes, in this area, definitely it needs to be included in the planning, in the management, and you need to be aware of it when you put your conceptual model together.
Okay, thank you. very much, Nicolette. Any other questions that would anybody like to pose to Nicolette? Nicolette, from my side, I would like to ask you a question in regards to your conceptual model. Do you think that you need to you need to have a model, numerical model that you need to build um, and change that on a regular basis, or how do you see it on to going forward with the conceptual model?
Fairness, I would have loved to build a conceptual model, but my brain has gotten tired. I don't want to learn modeling. One of the best models that I've seen so far is one that Ellen Zeiler did for this area. And one of the reasons why it was good is she sat with me and listened to some of my explanations, and she built in a lot of that into what I've said. So I would probably ideally sit with someone that knows how to do it and explain some of my observations, and maybe we can come up with something that's very good. But it's never going to be an exact replica of the real system. So it will have to be changed as new information becomes available. Otherwise, you might make management decisions based on your model that turns out to be completely wrong for your system.
Thank you. Is there anybody else that would like to ask Nicolette? I see there's someone, Joseph, also posed a comment in. Number of people is actually congratulating you on this, on the presentation. Joseph said, thank you so much for your highly informative talk. What is your strategy when you complete your hydrocensus? The reason I ask this is because when I knock on a gate where I should ask if they have boreholes, people tend to say no. But then you see beautiful flowers, other vegetations in the place. I always suspect that the answer given was not correct.
One of the most telltale signs of a borehole being on a property, especially in the Western Cape, is iron stains on the walls. In Cape Town itself, Cape Town has a registry. It's not completely up to date because its registration of your borehole is voluntary at this stage. So, but that, if you're working in Cape Town, that's one of the first places where you can go and look for additional information. Unfortunately, they're only registered by address, and it's not always easy to get to the right location. But if you do your hydrocensus during the day, you'll often find that the people are not at home. Hydrocensus is actually quite difficult because there's a mistrust often with people, and they don't want to provide the information because they're afraid that it's going to be used against them at some stage. That's why it's important to explain to them that it is possibly to their advantage. One of the farmers in this area had a borehole that he used for a bit of irrigation, and my predecessor asked him to put up a meter so that we can monitor its volume. And I went to him and I shared some of the monitoring data for the boreholes that's on his property. And I explained to him that putting up the meter will be to his advantage because it will tell us who is abstracting from the aquifer and possibly causing damage. So if you can find a way to explain to the person that you're encountering during your hydrocensus why it might be to their benefit. One of the advantages in this case would be, then we can provide you with some feedback on the number of abstractions in the area, and you can have some idea of what can impact your borehole. They might be more agreeable to allow you onto their property. But most often it takes time, it takes building a relationship and building trust. And when you're doing a hydrocensus, you don't have that time. So sorry, you will have to miss some of the data points. And the NGA is not up to date either. So yes, it's like Cape Town's database, just an additional tool that you can use during your hydrocensus.
Thank you, Nicolette. There's another question from Jane Gous that's saying, with regards to land use, I assume you would also need to include the effects of mining as well, especially if the mining is using groundwater and some of the water is recharging into the aquifer.
In this area, very definitely, the Elandsfontein phosphate mine is smack bang in the middle of a very important paleochannel aquifer system. But there is ways to handle the situation so that you do not cause long-term permanent damage. But yes, you need to include mining into your considerations for your conceptual model, for your management decisions, for everything that you do around your aquifer system. And it depends a lot on how vulnerable your system is to degradation.
Okay. There is 3 more questions. The first one is, at times of challenging components to obtain when dealing with conceptual modeling and water balance is evapotranspiration. Do you think it is trench mass if I do not use such data in my water balancing and conceptual modeling?
Evapotranspiration is difficult to get. If you want that data, you have to do the experiments yourself, or you have to rely on data for stations that's not nearby. One of the things that you need to remember with evaporation in this area, because of the fact that it's a winter rainfall area, you have hot, dry summers, which means your potential for evapotranspiration is highest in summer. But one of the other things that happens is your water levels drop in summer. So the buffer between the top of the soil and the water table is bigger. And the only thing that waters some of the plants at the top of the dunes is mist, which means the link between the water table and the vegetation is also smaller. So your potential evaporation is high, but the actual evaporation is not quite as high. So it throws a bit of more complexity into the system, but yes, evapotranspiration is a bit of a problem to get data. You can motivate when you put together your water balance why you didn't use the component, and then you can make assumptions and put it in and say, this is the assumptions I made because I don't have the data for it.
Okay. Second last question that we have is then, did you, in addition to water level data, was 70-hour aquifer tests conducted on the boreholes in the well field? This is especially helpful in determining the specific characteristics of the aquifer. 72-hour test is also good for revealing geological flow boundaries.
The original model that was built for this area was based on a longer pumping test of the well field. I don't have the data offhand at this stage, but it was because of that pumping test data that they said the drawdown will only be 5 meters. There's a difference between the data that comes from a pump test and long-term abstraction. It's only when you do long-term abstraction that you really get an idea of what your aquifer system is capable of. your pump test actually just tells you the short-term effects of your abstraction. It tells you what size of pump to put in, what size of infrastructure to plan for, and things like that. It actually does not tell you exactly how the aquifer or your groundwater system will react to long-term extraction. Yes, it has its place. We need to do it. There's cases where I have recommended that shorter pump tests would be acceptable if they do proper monitoring afterwards, because that monitoring afterwards tells you whether your management practice that you put in place based on your pump test is working or not, and whether you need to adjust it.
Okay. Thank you, Nicolette. There was just a very good comment from Kamal that was saying that the local information is so crucial. We'll provide that comment back to you. Then I'm going to close this this talk this afternoon, and thanking everybody that attended, and especially Nicolette for sharing your expertise with us. Please be on the lookout for our debrief and the presentation. I presume that will be distributed afterwards, and you can go to the website and for our debrief. Thank you very, very much, and be on the lookout for our next talk. Thanks a lot.